Hello students, in this video we are going to see a new chapter, that is monotonicity. First of all, let's try to understand what is the meaning of monotonicity. It is property of a function which is either increasing or decreasing in its domain. Let us consider a graph of a function. This function is increasing, so this is a monotonic function. This function is decreasing, so this is a monotonic function. If I consider graph like this, then this is not a monotonic, because this function is initially it is increasing, then decreasing, then increasing, so it is not a monotonic function. Now let's see different types of monotonic function. First is strictly increasing function. Let us consider this graph. Let's take 2 points on x-axis. Suppose this point is x1 and this point is x2, and corresponding value on y-axis. For x1 it is f of x1, and for x2 it is f of x2. Here x2 is greater than x1. Then we find that value f of x2 is greater than f of x1, and we find that this relation is true for all x that belongs to set of domain of the function. Then such function is called strictly increasing function or monotonically increasing function, and this becomes the condition for function to be strictly increasing in its domain. Now let's see different graphs of strictly increasing function. In this graph we find that derivative of the function is positive for all x that belongs to set of domain of the function. Now let's see this graph. This graph is also strictly increasing. This graph is also strictly increasing. At this point the derivative of the function is 0. For this graph derivative is positive, and also for this graph derivative is positive for all x that belongs to set of domain. Now let's take another graph. At this point derivative does not exist, or we can say function is not differentiable, and also at this point function is not differentiable. Then also it is a strictly increasing function because it is fulfilling the condition of strictly increasing function. Now let's see this graph. We find that this graph is discontinuous at this point. Then also this function is strictly increasing. Now let's see strictly decreasing function. Let us consider this graph. Now let us consider 2 points on this x-axis. Suppose this point is x1 and this point is x2, and corresponding value on y-axis. For x1 it is f of x1, and for x2 it is f of x2. So here x2 is greater than x1, but value for x2 is less than value for x1. So f of x2 is less than f of x1 for all x belongs to set of domain of this function. Then such function is called strictly decreasing function. Okay, and also this becomes a condition for a function to be strictly decreasing function. Now let's see different types of decreasing function. This is strictly decreasing function. This is again strictly decreasing function. This is also strictly decreasing function. Here we find that at this point function is not differentiable, but it is fulfilling the condition of strictly decreasing function, that for x2 greater than x1, f of x2 is less than f of x1 for all x that belong to set of domain of the function. Also we find that here the derivative is negative, here also derivative is negative for all values that belongs to set of domain of this function. Okay, we can have more graph which can be strictly decreasing function. And this graph is discontinuous, but it is strictly decreasing. So from these many graphs we find that for function to be either strictly increasing or strictly decreasing, function need not to be continuous or differentiable. In fact, graph must satisfy the condition of strictly increasing when we are saying that function is strictly increasing, or condition of strictly decreasing when we are saying that function is strictly decreasing. Okay, now let's see increasing function and decreasing function. For this, let's consider a graph. Now let's consider 2 points on x-axis. This is point x1, this is point x2. For x1 the value is f of x1, and for x2 value is f of x2. Okay, so here x2 is greater than x1, value of x2 is greater than or equal to f of x1 for all x belong to set of domain of the function. Now let's try to understand this statement, why we have taken here equal to sign. We can have value f of x2 greater than f of x1 or f of x2 is equal to f of x1. Now if we focus in this region for any x, f of x2 is equal to f of x1. The values are going to be equal for different x in this region. Okay, and if we compare the x from this region or this region, we find that f of x2 greater than f of x1. So we have two cases. We can have either f of x2 is equal to f of x1 or f of x2 is greater than f of x1. And if this condition is fulfilled, then function is increasing function. Now let's see decreasing function. Let's take a graph. Now let's take any 2 point on x-axis. Suppose this point is x1 and this point is x2. Corresponding value is for x1 it is f of x1 and for x2 it is f of x2. So from graph we find that if x2 greater than x1, we have f of x2 less than or equal to f of x1 for all x that belongs to set of domain of the function. Okay, see here we have taken here f of x2 less than or equal to f of x1. Why so? If we focus for x in this region, we find that f of x2 is equal to f of x1. For all the x in this region, we have f of x2 is equal to f of x1, means values are going to be equal in this region. And if we now focus in this region, x for this region and x for this region, we find that f of x2 is less than f of x1. Okay, and if this condition is fulfilled, then function is said to be decreasing function. See here we have here x which are infinite in this region, and for infinite x which are uncountable, we cannot count how many x are in this region. And we have such situation where for infinite x which are uncountable and f of x2 is equal to f of x1, then function is not strictly decreasing. In fact, function becomes simply decreasing function, right? Let's try some question based on graph. We have to identify the function as either strictly increasing or strictly decreasing, increasing or decreasing, or neither increasing nor decreasing. Okay, first question is f of x is equal to x. So graph of this function will be like this, which is equally inclined to both the axis, x-axis and y-axis, and passing through origin. We find that this function is strictly increasing. Okay. Next question, f of x is equal to x square. Okay. Graph of this function will be like this, that will pass through origin and concave upward. Okay, and symmetrical about y axis. We find that for all x that belongs to domain of this function is neither increasing nor decreasing, because in this part function is decreasing and for this part function is increasing. Okay, if we talk about if we talk separately, if we talk for x from minus infinity to 0, the function is strictly decreasing, and for 0 to infinity function is strictly increasing. Okay, now let's see this question, f of x is equal to x cube. Okay, the graph will be like this, will pass through origin, and this part will be concave upward and this part is concave downward. So this function is strictly increasing. Reason is for all x that belongs to domain of this function, we have f of x2 greater than f of x1. Okay, this function is strictly increasing. Though we find that derivative of the function is 0, but this point is countable point. If we had here uncountable points or infinitely many points where derivative is 0, then function would have been simply increasing function. Okay, question number 4. Now let's see this question, fx is equal to mod x. The graph of this function will be like this, like this. So if we find that for this part of the graph the function is strictly decreasing, and for this part of the graph function is strictly increasing, and for all real x the function is neither increasing nor decreasing. Next, let's see fx is equal to root x. The graph of this function will be like this. We have a value at x equal to 0, which is 0, and it is going like this. We find that this function is strictly increasing. Okay, Now let's take another question. F of x is equal to 1 by x. So graph of this function is like this. In third quadrant it is like this. We find that for all real x this function is neither increasing nor decreasing, but for x for minus infinity to 0 it is decreasing function, and from 0 to plus infinity it is also decreasing function. In fact it is strictly decreasing function. Here also it is strictly decreasing function, right?